From a dark hillside, the night sky can still look ancient, quiet, and almost perfectly unchanged from hour to hour. That appearance is convincing because human eyes are poor at noticing most of the subtle changes happening above us. Stars brighten, galaxies flare, asteroids shift, and distant explosions rise and fade beneath an otherwise familiar pattern of light. Modern astronomy increasingly treats that pattern not as a picture, but as a signal that can be compared over time. For much of observational history, astronomers worked in a slower rhythm shaped by photographic plates, scheduled nights, and later analysis. A telescope gathered light, researchers carried the measurements away, and the deepest interpretation often came long after the observing run ended. Even with electronic detectors and digital archives, many major surveys were designed around datasets released in large periodic batches. That cadence remains scientifically powerful, especially when researchers need carefully calibrated measurements accumulated across months or years. But the sky has always contained events that refuse to wait for the next convenient release. A supernova can brighten rapidly, a gamma-ray burst can vanish, and a near-Earth asteroid can move noticeably between visits. Long before Rubin, astronomers built alert networks and transient surveys to warn one another about such time-sensitive changes. Gamma-ray satellites, gravitational wave observatories, and optical surveys already proved that fast notices could redirect telescopes toward fleeting targets. The Zwicky Transient Facility, for example, demonstrated how a wide-field optical survey could generate enormous streams of transient alerts. Other networks learned to distribute coordinates and probabilities quickly enough for independent facilities to decide whether follow-up was worthwhile. So Rubin did not invent real-time astronomy, and its story becomes more interesting when that history is kept intact. What Rubin changes is the scale at which rapid optical change becomes a normal, nightly condition of doing astronomy. The Vera C. Rubin Observatory sits high on Cerro Pachón in Chile, built to repeatedly photograph huge regions of southern sky. Its central instrument, the LSST camera, contains about 3.2 billion pixels and records an exceptionally broad view. One exposure covers about 9.6 square degrees of sky, an area enormous by the standards of deep astronomy. That combination of width and sensitivity lets Rubin collect many different kinds of cosmic objects within each exposure. The survey does not rely on a single majestic image taken once and admired forever. It returns to the sky again and again, building a time sequence in which brightness and position can be compared. Standard visits use short exposures on the order of 30 seconds, allowing the observatory to move rapidly across planned fields. Night after night, those repeated looks create the raw material for detecting what changed since an earlier view. A changing star may be physically ordinary, yet its measured brightness can differ enough to matter to a particular analysis. An asteroid may not brighten at all, but its changing position can make it stand out against a previous sky image. A supernova may emerge where no comparably bright source appeared before, then evolve over days as the explosion develops. These very different behaviors all become part of the broader problem of recognizing change in a crowded, evolving sky. Rubin can collect roughly 10 terabytes of image data during a night, far beyond anything people could inspect one frame at a time. The practical observer is therefore not a person staring continuously at a monitor beside the telescope. Software must measure, compare, reject artifacts, identify qualifying changes, and package useful information fast enough for other systems to act. That requirement turns data processing from a later convenience into part of the observatory's immediate scientific operation. On February 24th, 2026, that behavior crossed an important public threshold. Rubin generated its first scientific alerts and sent them into a globally public stream available to the broader research community. The first night did not produce 7 million alerts, a distinction worth holding on to as the story grows larger. It produced roughly 800,000, already a volume far beyond any sensible model of individual human inspection. 800,000 notifications can sound like 800,000 discoveries, but that is not what the number means. An alert is a machine-generated notice that a measurable change or motion met the system's criteria for reporting. It tells downstream software and researchers that something in the new observation deserves computational attention and possible scientific interpretation. It does not by itself prove that the source is new, rare, important, or even astrophysically surprising. Among the first alerts were detections associated with supernovae, variable stars, active galactic nuclei, and objects moving through our solar system. Each category describes a different physical reason why the sky can look different from one visit to the next. A variable star may brighten repeatedly, while an active galactic nucleus can flicker as matter feeds a distant black hole. An asteroid can simply move across the background, changing where its light appears without becoming a new solar system body. That last point reveals why alert counts and object counts cannot be treated as the same thing. The same physical source can generate multiple measurements and may trigger more than one alert as Rubin revisits its field. Some alerts concern previously known kinds of behavior, and some may be scientifically unimportant for a particular research program. Rarity, relevance, and confirmation enter later, after the first machine-readable notice has already left the observatory's processing chain. The power of the alert is therefore not that it arrives carrying a final scientific verdict. Its power is that information about change can begin moving outward while the astronomical event itself may still be evolving. A rapidly brightening transient can be noticed soon enough for other facilities to consider observing it before crucial phases disappear. A moving object can be recognized as part of a changing pattern, while additional measurements are still capable of refining its path. Those possibilities depend on distribution because Rubin is only the first major station in a much larger chain. The public alert stream is designed for software systems around the world rather than for millions of manual notifications on astronomers' phones. Independent alert brokers receive the stream and help scientific communities filter, enrich, classify, and prioritize what they want to examine. Those brokers do not retroactively become the telescope, and their classifications are not equivalent to confirmed discoveries. A broker can help decide which alerts look promising for a supernova search, an asteroid study, or another specific program. A follow-up telescope performs a different job by collecting new observations after a candidate has been selected for attention. Spectroscopy, repeated imaging, or measurements from another facility can then add evidence the original Rubin alert did not contain. Scientific confirmation comes only after the relevant evidence and validation are strong enough for the claim being made. Keeping those stages separate matters because real-time astronomy moves quickly enough for their language to blur together. Detection can happen first, automated classification second, human or programmatic selection later, and confirmation later still. The sequence may vary by object class, but no responsible description should compress every step into the word discovery. Rubin's scale makes that discipline more important, not less, because enormous numbers magnify careless interpretations of what an alert means. There was another limitation during Rubin's first alert months that keeps the early 2026 story grounded. Detecting change through difference imaging requires a suitable template, a trusted earlier view of the same region for comparison. Before the first annual survey data release, those templates must be built incrementally from commissioning and early operational observations. As a result, the early alert stream cannot cover the full planned survey footprint at mature scale from the beginning. Rubin's early science program therefore describes alert production as a progressive ramp-up rather than an instant jump to final capacity. Template coverage expanded during the spring as additional areas reached the quality needed to support reliable automated comparison. In some regions and filters, useful templates existed earlier than in others, so alert production followed that uneven readiness. This is why the first 800,000 alerts should be seen as an opening stage, not the mature nightly ceiling. Then, on June 29, 2026, Rubin officially began the legacy survey of space and time. The 10-year survey turned years of construction and commissioning into a sustained program of repeated observations across the southern sky. Its purpose reaches far beyond transient alerts, including dark matter, dark energy, the Milky Way, and the inventory of our solar system. Yet the changing sky is where Rubin's new operational rhythm becomes easiest to feel in real time. The survey is designed to revisit vast areas repeatedly, turning separate exposures into something closer to a long astronomical movie. Most frames will not contain a once-in-history spectacle, and most changing sources will not become headline discoveries. The scientific value comes from measuring the ordinary and the rare within the same systematic stream of repeated observations. That consistency makes unusual behavior easier to recognize because it is compared against a much larger record of what usually happens. As template coverage and routine operations mature, Rubin's alert stream is expected to reach up to about 7 million alerts per night. That figure is a capacity-scale description of the system, not the number Rubin produced on its first scientific alert night. It is also not a prediction that 7 million important astronomical events will demand 7 million follow-up observations. The number describes the volume of machine-readable changes that may need sorting before anyone knows which subsets matter most. At that point, the limiting resource begins to shift from noticing change toward deciding what deserves attention now. No research team can read millions of alerts individually, and no network of telescopes can follow every candidate immediately. Different scientists care about different kinds of motion, color, brightness, history, location, and association with known objects. The same nightly stream must therefore become many smaller streams, each shaped by a scientific question and available resources. This is where astronomy starts to resemble a continuously triaged information system rather than only a sequence of observing campaigns. Periodic data releases still matter, because deep calibration and long baseline analysis answer questions that immediate alerts cannot. But alongside that slower rhythm now runs another one, optimized for changes whose scientific value can depend on acting quickly. The transition is not from old astronomy to a replacement, but from one dominant tempo to two working side by side. The apparent revolution, then, is not simply that Rubin sees more of the changing sky than earlier surveys. It is that millions of notices can leave the observatory while the night that produced them is still unfolding. Somewhere inside that flood, a source may be fading, brightening, moving, or doing something no filter expected to prioritize. Before anyone can decide what it is, the system first has to establish that something measurable changed at all. Picture one ordinary field filled with stars, galaxies, detector noise, and the accumulated light of a familiar patch of sky. Rubin returns to that field and records another image that looks almost identical when viewed as a whole. Yet one point of light is now different from the remembered sky, and that small difference is where the next chain begins. Between that new image and a public alert lies a hidden sequence of comparison, detection, measurement, and packaging. That single altered point of light begins inside an image containing far more information than any astronomer could inspect manually. Around it are stars, galaxies, faint sources, detector imperfections, atmospheric effects, and billions of measurements recorded during one visit. The first problem is therefore not deciding what the changed object is, but establishing that the change is measurable. To do that reliably, Rubin must turn a fresh exposure into something that can be compared with its remembered sky. Each standard visit lasts about 30 seconds, and captures close to 10 square degrees in a single enormous field. That wide view can contain countless ordinary sources surrounding the one change that eventually attracts scientific attention. Repeated hundreds of times across a clear night, the process contributes to roughly 10 terabytes of nightly image data. At that scale, automation is not merely faster than human inspection, because human inspection is no longer a workable alternative. The camera first produces measurements that still carry the fingerprints of the detector, telescope, atmosphere, and observing conditions. Prompt processing applies calibrations so that instrumental behavior is separated as carefully as possible from genuine astronomical light. Software also needs an accurate understanding of where the image lies on the sky and how measured brightness should be interpreted. Only then can the new visit be compared meaningfully with an earlier view of the same celestial neighborhood. Imagine our changed point sitting near the edge of a distant galaxy whose other stars appear essentially steady. The new exposure knows where those sources appear now, but change requires a second image that represents what came before. That earlier reference is the template, constructed to provide a reliable comparison for the same region and observing filter. Without an appropriate template, the pipeline cannot perform the same kind of automated difference analysis for that patch of sky. The new image and the template are not simply placed on top of each other like two transparent photographs. They must be aligned precisely enough that the same fixed celestial sources occupy corresponding positions in both views. Differences in atmospheric blurring and image quality must also be handled so ordinary stars do not masquerade as cosmic changes. This careful matching is what makes the next operation scientifically useful rather than merely visually dramatic. Once the images are prepared for comparison, the template is effectively subtracted from the new observation. A star that stayed equally bright should largely disappear because its earlier light and its new light cancel in the comparison. The steady glow of a galaxy should also be greatly reduced, leaving less distraction from whatever actually changed. What remains is called a difference image, a view designed to emphasize change rather than the familiar sky itself. Our hypothetical point now becomes easier to isolate because its brightness did not match the template at that location. If a source brightened, a residual signal can remain where the extra light appears in the new observation. If something faded, the subtraction can reveal that the new image contains less light than the remembered sky. The important concept is simple, even though the underlying processing is sophisticated. Unchanged light recedes, and differences become measurable. A moving object creates another kind of mismatch because its light appears at a different position from an earlier observation. An asteroid crossing the field can therefore produce measurable differences even when nothing unusual has happened to the asteroid itself. A variable star can reappear in this machinery repeatedly because changing brightness is part of its normal physical behavior. Difference imaging detects change first, while the physical explanation for that change remains a separate question. Unfortunately, a difference image can contain things that resemble astronomical changes without representing real changes in the sky. Detector defects, cosmic rays, imperfect subtraction, bright star effects, or difficult image boundaries can create suspicious residual patterns. Atmospheric conditions can complicate the comparison as well, especially when two observations differ noticeably in sharpness or transparency. So the pipeline must decide which residual detections satisfy its reporting criteria before constructing an alert. This filtering inside prompt processing is different from the later scientific filtering performed by community alert brokers. Rubin's immediate task is to identify and measure detections that meet the pipeline's criteria for entering the alert stream. It is not yet asking whether a particular research team considers that source exciting enough for scarce telescope time. That science-specific judgment belongs farther downstream, after the alert has been produced and distributed. For a qualifying difference image detection, the system measures properties that help describe what changed and where it happened. Position and brightness are fundamental, along with quantities describing the detection and circumstances of the observation. Those measurements transform a glowing residual from a picture into structured information that another computer can examine immediately. The result is no longer simply an interesting pixel pattern, but a detected source with machine-readable, measured properties. Rubin then constructs an alert packet centered on the detection that triggered the notice. The packet carries catalog measurements describing the source rather than merely announcing that an unspecified object changed somewhere. It can also include small image cutouts showing the new observation, the template, and the resulting difference around the source. Those compact views give downstream systems useful context without requiring them to begin by retrieving the entire enormous camera exposure. When available, an alert can carry information connected with earlier detections and measurements associated with the same changing source. That history matters because one isolated brightness measurement often says much less than a pattern developing across repeated visits. A rising sequence might resemble an emerging transient, while repeated oscillations could point toward familiar stellar variability. Even then, the packet supplies evidence and context rather than a final declaration of what the object physically is. This distinction becomes especially important when the same source changes again on another night or even another visit. A known variable star does not become newly discovered every time its brightness crosses a reporting threshold. An active galactic nucleus can fluctuate repeatedly and generate fresh measurements as Rubin returns to the same region. Each alert can be useful because it extends the time record even when the underlying object is already familiar. Moving objects make the distinction between alerts and unique objects even easier to see. An asteroid can appear at one position, move across the sky, and produce additional detections during later observations. Connecting those detections into an object and determining an orbit requires analysis beyond the existence of any single alert. One physical body can therefore contribute multiple notices while the scientific story develops across time. This is the numerical correction hidden inside the headline of 7 million alerts per night. 7 million alert packets would not imply 7 million unique astronomical objects appearing for the first time. They certainly would not imply 7 million extraordinary discoveries waiting for telescopes to confirm before sunrise. They represent a vast stream of qualifying changes from which scientifically valuable subsets must later be identified. Speed matters because some of those subsets contain events whose most revealing phases may last only briefly. Rubin's prompt processing system is designed around a real-time alert latency of roughly 60 seconds after image readout. That operational goal is best understood as a system requirement, not a promise that every early alert follows an identical stopwatch. Public descriptions of the first scientific alerts also used a broader window of roughly 2 minutes from image capture. Either way, the essential change is that processing happens on the timescale of the observing night rather than months later. The telescope can move toward another field while data systems are already processing what the previous exposure contained. As the night advances, observation and interpretation begin overlapping instead of occurring as completely separate phases. That overlap creates the possibility of responding while a transient is still brightening, fading, or otherwise changing. Once Rubin has constructed an alert packet, it distributes that packet outward through the World Public Alert Stream. At this stage, Rubin has reported a qualifying measured change and supplied information that downstream software can evaluate. It has not decided whether that particular alert belongs on a supernova researcher's short list for immediate follow-up, nor has the alert packet itself confirmed the physical identity of the source that produced the changing signal. That boundary is one of the most important lines in the entire real-time astronomy system. Rubin observes, processes the image, detects qualifying difference sources, measures them, constructs alerts, and distributes the resulting stream. Independent brokers receive those alerts afterward and apply additional logic designed around the needs of different scientific communities. A broker can enrich and prioritize the information, but doing so is a downstream layer rather than Rubin's original detection step. A broker might compare an alert with external catalogs, examine its previous behavior, or estimate what type of source seems plausible. Those operations can make the packet far more useful to a researcher searching for one particular class of event, but a classification score produced by software is still an inference based on available evidence, not a final physical confirmation. If more evidence is needed, a selected candidate may later be sent toward another telescope for follow-up observation. That later telescope is not confirming the object merely by pointing at it either. It may gather spectra, additional images, or repeated measurements that reveal properties missing from Rubin's initial alert. Scientists then interpret that enlarged body of evidence according to the standards appropriate for the phenomenon involved. Detection, broker classification, follow-up observation, and confirmed interpretation remain connected stages with different responsibilities. Now return to the scale that made this division of labor necessary in the first place. Even a fraction of millions of nightly alerts would overwhelm any attempt to evaluate them one by one. The Firehose has to be read by machines before human attention can be concentrated on a manageable number of candidates. The problem has changed from finding any changing source to finding the right changing sources for a particular question. A supernova team may want young explosive transients, while another group may care about unusual stellar variability. Solar system researchers may search for patterns of motion, while anomaly hunters may value sources that fit familiar categories poorly. All of them can begin with the same Rubin stream, yet each needs a radically different view of what deserves attention. The next instrument in this chain is therefore not another mirror, but a broker network that turns one Firehose into specialized scientific feeds. The raw Rubin stream now arrives at a boundary, where one enormous flow can begin separating into many different scientific questions. No single researcher needs every changing star, every moving asteroid, and every possible explosion crossing the stream. What each research program needs is a way to ask the Firehose for a much smaller and more useful subset. That is the job of the alert brokers, independent software systems positioned downstream from Rubin's public alert distribution. 7 full-stream brokers are configured to receive and process the complete legacy survey of space and time alert stream. They are Vera C, Ampel, Antares, Babamul, Fink, Lasserre, and Pit Google. Receiving the full stream demands substantial computing, storage, networking, and operational reliability before any specialized science even begins. That is one reason Rubin distributes the complete Firehose to a limited set of systems, rather than expecting every scientist to ingest it. 2 additional systems, SNAPS and POI Broker, operate downstream without needing direct access to every Rubin alert. They can receive selected subsets through partnerships with full-stream brokers because their science goals do not require the entire river. That architecture contains an important lesson about scale before any machine learning model enters the story. Useful astronomy does not require copying every possible event into every laboratory that might eventually care about one. A broker can begin with rules simple enough to explain without knowing anything about advanced artificial intelligence. A scientist might ask for sources brighter than a chosen threshold and detected for the first time only recently. The same filter might require previous detections so that one isolated measurement does not dominate the candidate list. Another rule could limit the search to a certain region of sky or reject sources already associated with familiar objects. These conditions are valuable because scientific interest depends on context rather than brightness alone. A faint new point inside a nearby galaxy may matter more to one project than a brighter variable star already well understood. A rapidly moving source may be irrelevant to a supernova search while becoming exactly what a solar system program wants. The alert itself has not changed, but the question being asked of that alert has. Brokers become more powerful when they connect Rubin measurements with information that already exists elsewhere. A sky position can be compared against catalogs of stars, galaxies, active galactic nuclei, and sources observed at other wavelengths. An apparent transient near a known galaxy can therefore acquire contextual information that was not the purpose of Rubin's detection step. A source coinciding with a known variable star can likewise be treated differently from an isolated change with no obvious match. Time adds another dimension because brokers can assemble the changing history of a source across repeated measurements. That sequence of brightness measurements forms a light curve, one of the basic fingerprints of time domain astronomy. Some light curves rise quickly, some pulse repeatedly, and others wander irregularly across months or years. Those patterns can provide clues about what kind of physical system might be producing the observed changes. This is where statistical models and machine learning can help sort patterns far faster than people could compare them manually. A broker may estimate probabilities for different source classes based on colors, light curve shape, context, and previous measurements. Another system may search for anomalies, emphasizing objects that resemble the familiar population less closely than expected. These outputs are rankings and inferences, not certificates revealing the true physical identity of every source. A high probability of being a supernova means the available evidence resembles known supernova behavior under the model being used. It does not mean the software has performed the additional observations needed to establish a definitive classification. That uncertainty is not a flaw in the broker concept because prioritization is precisely what probabilities are useful for. A telescope schedule does not need mathematical certainty before deciding that one candidate deserves a closer look. Now imagine 3 research groups watching the same night through 3 very different broker filters. One group wants rapidly rising sources near galaxies because its program is searching for young supernova candidates. Another watches variable stars for unusual behavior that departs from each star's established pattern. A third may focus on moving solar system sources whose positions and histories make them relevant to its own investigation. Each group can receive a relatively small feed even though all 3 feeds ultimately descend from the same Rubin stream. The broker layer therefore changes the meaning of access from receiving everything to receiving what can actually be used. The 7 full-stream brokers do not need to behave identically because different architectures can serve different scientific communities. Vera C emphasizes aggregated and classified light curves along with machine learning probabilities across many categories of variable phenomena. Antares can attach contextual catalog information and run filters ranging from simple magnitude cuts to more sophisticated models. Think combines filtering, cross-matching, feature construction, and machine learning modules that can be customized for particular science cases. LSST allows filters to use light curve properties, sky geometry, and contextual associations with known astronomical populations. Babamul is designed to break the massive stream into lighter channels organized around useful properties of astronomical events. Google approaches the problem through scalable cloud infrastructure intended to distribute and analyze alerts with low latency. Ampel provides another full-stream pathway for evaluating alerts and building science workflows around changing astronomical sources. The point is not that one broker contains the correct view and the others contain competing versions of reality. They are different instruments for interrogating the same fast-moving observational stream according to different needs. That becomes easier to understand when we follow an actual early Rubin demonstration through several pieces of this ecosystem. During an end-to-end Neuer Lab run, Antares examined incoming Rubin alerts and flagged 18 as likely supernovae. The wording matters because likely supernovae were candidates produced by filtering and classification, not 18 already confirmed explosions. The broker had performed its job by reducing a much larger stream to targets whose properties justified additional attention. Those selected targets then entered another system called the Gemini Observation and Analysis of Targets System, or GOATS. GOATS provides a place to select targets for follow-up and turn that decision into observation requests for compatible facilities. This step is neither the original Rubin alert nor the broker classification that brought the candidate to attention. It is the operational bridge between deciding that a target deserves more evidence and actually asking a telescope to collect it. Those requests can move into the Astronomical Event Observatory Network, known as AEON. AEON links software and participating observatories, so transient targets can be inserted into flexible observing workflows. Its participating facilities span different telescope sizes, instruments, locations, and observing capabilities rather than duplicating one another. That diversity is valuable because no single instrument can answer every physical question raised by a changing point of light. The demonstration used the dark energy camera on the Victor M. Blanco 4-meter telescope in Chile. Blanco imaging could provide additional measurements of how selected sources looked and changed after Rubin first triggered attention. The SOAR telescope on Cerro Pachon contributed observations with its Goodman spectrograph. Both Gemini North and Gemini South also participated using their Gemini multi-object spectrographs. Las Cumbres Observatory added imaging from its 1-meter and 2-meter telescopes to help trace changes in brightness over time. Those repeated measurements could extend a light curve beyond the information available when the initial alert entered the system. A light curve reveals how brightness evolves, but spectroscopy asks a different question by spreading an object's light into wavelengths. Patterns in a spectrum can reveal signatures of chemical elements, velocities, temperatures, and physical conditions within the source. For supernova candidates, those details can help distinguish different families of stellar explosions that may look similar photometrically at first. That information was never missing because Rubin failed at its task because the original alert was designed for another task. Rubin had reported the changing source rapidly, allowing specialized instruments to decide whether deeper characterization was worth the cost. The follow-up network then supplied measurements chosen specifically to answer questions the alert packet could not settle alone. This division of labor makes real-time astronomy look less like one giant telescope and more like a coordinated nervous system. Rubin senses widespread optical change, brokers sort the signals, and follow-up facilities examine selected targets with different capabilities. Software can even carry an observation request across much of that chain without requiring someone to rewrite coordinates by hand. Automation shortens delays, but it does not create unlimited observing capacity at the far end of the system. A large telescope can observe only one limited set of targets during any available stretch of darkness. Weather, target visibility, instrument configuration, existing programs, and scientific priority all constrain what can happen next. The alert Firehose may contain millions of opportunities, while access to an 8-meter telescope remains measured in precious hours. That mismatch turns prioritization itself into a central scientific and operational problem. Gemini created one program that makes this scarcity unusually visible in the Rubin era. The Once in a Rubin Gem initiative reserves 120 hours across 3 years for exceptionally compelling LSST alert targets. The program is intended for rare or scientifically critical phenomena whose value could diminish if rapid observations are missed. It even creates room for unexpected targets that may not fit neatly inside ordinary advanced planning. But reserving scarce time still does not remove the need to decide which alert deserves that extraordinary opportunity. The better the detection system becomes, the more consequential that selection problem can become. A broker can rank a candidate highly, but probability alone cannot manufacture the missing physical evidence. Goats can send an observing request, but scheduling a telescope does not prove the source belongs to the predicted class. A spectrum can add decisive clues, yet even those measurements must be reduced, interpreted, compared, and validated appropriately. Real-time astronomy accelerates the journey toward evidence, but speed does not erase the distinction between suggestion and conclusion. One promising candidate has now traveled from Rubin's alert stream through software triage and into a second telescope. The final question is what additional evidence turns that rapidly generated notification into a defensible astronomical discovery? Our candidate has reached another telescope, but additional photons do not automatically turn a promising classification into a discovery. The new observations have to answer questions appropriate to whatever physical phenomenon scientists think they may be seeing. That means astronomy has no single universal confirmation step waiting at the end of every alert pipeline. A stellar explosion, a moving asteroid, and a neutrino-linked transient demand different kinds of evidence before strong claims are justified. For a supernova candidate, repeated imaging can establish how the source brightens and fades across the surrounding days. Spectroscopy can reveal broad patterns in the light that distinguish one family of stellar explosion from another. Its position relative to a host galaxy may add another layer of evidence about distance, environment, and likely origin. Several measurements together can support an interpretation that no single alert packet was designed to establish alone. Even then, scientists still have to reduce the observations, evaluate uncertainties, compare alternatives, and report the result responsibly. The speed of the initial detection changes how early that work can begin, not the standards needed for the final conclusion. A broker probability can guide attention, while later evidence determines whether the suggested interpretation survives closer examination. Real-time astronomy shortens the distance between suspicion and evidence without erasing the scientific space between them. Solar system discoveries make this phenomenon-specific logic especially clear because the central problem is often motion rather than changing brightness. A point detected in one exposure may be an asteroid, but a single position usually tells us little about its path. Additional detections at different times reveal motion against the background stars and begin defining a trajectory across the sky. Those measured positions can then be linked into a track that represents one physical body instead of several unrelated detections. From that track, astronomers can begin fitting an orbit and testing whether future observations appear where the predicted path says they should. The process can require more measurements as the observing arc grows and uncertainties in the orbit become better constrained. This pathway is fundamentally different from obtaining a spectrum of an exploding star, even though both stories may begin with rapid detections. For moving objects, association across observations and orbit determination are central parts of turning detections into defensible astronomical objects. The Minor Planet Center provides the international clearinghouse where observations of small solar system bodies are collected and maintained. There, positional measurements from Rubin can join observations from other facilities rather than remaining isolated inside one survey. That wider observational record supports identification, orbit refinement, provisional designations, and the continuing catalog of known minor bodies. A moving detection, therefore, becomes scientifically durable through association and repeated positional evidence, not through one alert appearing dramatic. Rubin's early operations quickly demonstrated how powerful that repeated wide-field coverage could become for solar system science. By the early survey era, Rubin observations had contributed more than 11,000 previously unknown asteroids. That early population included 33 near-Earth objects and hundreds of bodies orbiting beyond Neptune. Those numbers describe identified populations built from linked observations, not thousands of individual alert packets magically becoming discoveries. Near-Earth objects also illustrate why confirmation can become an iterative process rather than a single final moment. An early orbital solution can improve as new positions extend the measured arc and reduce uncertainty about future motion. A newly identified body may therefore become better understood over many observations after its first appearance in survey data. Discovery is not always a dramatic instant because sometimes it is the point where enough linked evidence becomes convincing. That same principle appears differently when the first signal comes from outside Rubin entirely. So far, we have mostly followed information outward from Rubin toward brokers and other telescopes, but a modern observatory must also be capable of receiving urgent information generated somewhere else in the scientific network. In 2026, Rubin carried out its first target of opportunity response to an alert originating with IceCube. IceCube detects high-energy neutrinos using a vast instrument embedded deep within Antarctic ice. A neutrino event can point astronomers toward a region where an energetic astrophysical source may be active. In that situation, Rubin is no longer the observatory shouting first that something changed in visible light. Instead, an external messenger tells Rubin where something interesting may be happening and asks the optical sky for additional evidence. This reverse information flow reveals how incomplete it would be to describe real-time astronomy as one telescope broadcasting alerts. The deeper architecture is a network in which observatories can alternate between detecting, receiving, responding, and supplying complementary measurements. Neutrinos are especially valuable because they carry information through environments that light may not escape in the same way. Optical observations provide a different view, potentially revealing galaxies, transients, or other visible changes associated with the same region. Neither messenger automatically identifies the source because association must still be evaluated against timing, position, and competing explanations. A coincident optical transient can be intriguing without proving that it produced the neutrino that triggered the search. Multi-messenger astronomy gains power precisely by combining independent forms of evidence while preserving uncertainty about their physical connection. The challenge is to determine when separate signals truly belong to one event rather than merely sharing a patch of sky. That requires coordination among instruments, measuring different physical messengers on different schedules and with different uncertainties. A neutrino alert can trigger optical imaging, while an optical transient can motivate observations at radio, X-ray, or other wavelengths. Gravitational wave detections can create another urgent search problem because the source may fade quickly across a broad localization region. Wide-field surveys become valuable partners because they can search large areas for changing optical counterparts while the event is still young. The same real-time machinery can therefore serve both directions of scientific traffic across the observatory network. Rubin can generate a notice that sends other telescopes outward, or receive an external trigger that changes where Rubin looks. That two-way behavior makes the modern observatory part of a responsive system rather than an isolated producer of images. Yet even this rapid network represents only one of the two major tempos now operating inside Rubin science. Prompt products answer questions that become less useful if scientists have to wait months before learning that something changed. They emphasize speed, recent measurements, and the ability to root attention while a time-sensitive phenomenon may still be observable. But many of Rubin's deepest questions depend on something almost opposite: a carefully accumulated record processed with broad consistency. Those questions benefit from larger collections of observations, improved calibrations, and long baselines that reveal populations rather than isolated moments. This slower layer appears through accumulated data products and periodic releases rather than through the immediate alert stream. By 2026, Rubin users were already working with data previews designed to support analysis before the first full annual survey release. Data Preview 2 arrived in July 2026 as another step in that slower accumulation of process survey information. The first complete annual legacy survey of space and time data release still lies later in the survey program. That timing does not make the slower products obsolete because they are designed to answer different kinds of questions. An alert can say that this location changed recently, while a deep release can describe how entire populations behaved across accumulated observations. A prompt stream favors immediacy, while a periodic release favors uniformity, depth, long baselines, and large-scale statistical analysis. Neither rhythm replaces the other because the changing universe contains both urgent events and patterns that reveal themselves slowly. A supernova may demand immediate spectroscopy, while dark energy studies depend on carefully controlled measurements accumulated across enormous samples. A fast-moving asteroid may require timely positional follow-up, while a stellar population study may benefit from years of repeated photometry. Rubin's importance, therefore, comes partly from operating at both speeds within one long survey of the changing sky. One system asks what changed now, while another asks what the accumulated record means when thousands of nights are considered together. The 7 million alert headline belongs to the fast side of that story, but its meaning becomes clearer after following the entire chain. Those millions are not millions of final conclusions and not millions of rare phenomena demanding immediate 8-meter telescope time. They are millions of machine-readable opportunities to ask whether a measured change belongs to a scientific question worth pursuing. Some will describe familiar variability, some will trace moving objects, and some will point toward genuinely rare events. The scientific achievement is not that every packet matters equally, but that useful differences become searchable before the night is over. Brokers can reduce the flood, follow-up facilities can add evidence, and specialized communities can apply their own standards of validation. The observatory has therefore changed more than the amount of sky that can be photographed efficiently. It changes how quickly observations can become questions for other machines, other telescopes, and eventually other scientists. In that architecture, the telescope is only the beginning of a chain that includes computation, context, scheduling, measurement, and judgment. Real-time astronomy is therefore as much an organizational transformation as it is a triumph of cameras and computing. Observatories that once operated as mostly separate instruments increasingly participate in shared streams of coordinates, probabilities, priorities, and requests. The changing sky becomes a common workspace where evidence can move between facilities almost as quickly as attention can be reassigned. And that brings the story back to the original problem hidden beneath the spectacle of scale. When detecting change becomes routine at enormous volume, the difficult question becomes which changes deserve deeper evidence before their opportunity disappears. That question cannot be answered by the camera alone, because scientific value depends on context, uncertainty, resources, and the goals being pursued. The 7 million alert sky is therefore best understood as a searchable opportunity space rather than a nightly catalog of 7 million discoveries.
The deeper shift here is not that machines have replaced judgment, but that judgment now begins much earlier in the data flow. When detections become abundant, attention becomes scarce, and every filter quietly expresses a choice about which possibilities deserve limited time. That makes prioritization part of the scientific method itself, because telescope hours, validation effort, and human focus cannot expand without limit. The challenge is therefore not merely to notice more change, but to spend evidence wisely enough that speed still leads to understanding.
Outside, the night sky still looks almost motionless to anyone standing beneath it. But behind that quiet appearance, stars pulse, explosions brighten, asteroids move, and distant systems change from one observation to the next. Rubin turns those differences into a living stream that can be measured, sorted, questioned, followed, and eventually understood. The sky did not suddenly become restless when Rubin began watching it, because astronomy finally learned how to listen while it changes.